All right, amazingly. Let's get rolling. Number one, I think this is all actually working now. Um, if you jump on Discord, I haven't yet. I got to keep tweaking, but we should be streaming on YouTube and on Discord right now. Can I just get randomly just check each one of those? And it's a configuration that takes me like a solid 10 minutes just to execute on it. Um, but I've also got my headphones in because that becomes the audio feed into the stream, which goes to Discord and goes out to YouTube. When I did it on Tuesday, we had no audio. Professor Fahim in the other section was threatening to do like a bad overdub or like a bad lip reading overdub of my video because there was no audio. I'm like, the only rule I have on that is you would have to like share with me later on. So, anybody on Discord, can you see it, hear it, looking okay?
It works perfectly both in Discord and YouTube.
Okay, and other confirm on YouTube. We're streaming. We're okay. And then what I'll do is let me drop the link from YouTube into the Discord chat. My original idea was to set the thing up, and I still can, so that what we saw projected up here was actually the OBS stream, um, which we can still do it. And I'm not sure what's ideal, honestly. This is so much easier just when everybody just stays home, you know? And I'm not recommending that. I'm just saying. All right. So I just dropped the link to the YouTube stream, and that's good. I mean, again, there's actually a risk, honestly, with a class like this, that there's a certain cross section that'll be like, I'll just watch it on YouTube, and then they're never going to watch it. And it's going to be the lowest priority, and then homework bingo's falling off, and then they're toast. And I can't change all diapers, so we're just going to roll. And I still think it's valuable for you guys when you do, first of all, I think there's one student at least in one of the two 2810 sections that's positive for COVID right now and has no choice to be here, And if anybody else feels uncomfortable, a little under the weather, whatever, it's kind of ideal. So we're just going to keep doing that. So the real question, so what you see, what I can do, let me see if I can. Let me see. Nah, I'm not going to mess. But here's a question. Would you rather have like Discord chat on this screen that you see here live in class, or does it matter because you can just see it on Discord if you want to? You know what I mean? Just leave this clean. Well, well, and when I tried to do it before, it came out just so small. I mean, trying to read what's going on the Discord thing, and I can't really see it that well anyway. So the only gotcha is for me. I'm not really seeing the Discord chat, but it is really handy. For I think to drop comments and have a place. So we're talking about general dash doctor dot k dash k, which somebody called General K, which I like that because it makes me feel like I have a lot more authority. General K. Okay, so I think we're good. I need like a technical director to just set everything up. It's also odd to lecture with the headphones. I don't walk around talking to people with these in, but I think it's the cleanest way to get solid gold sound coming everywhere. So that's what we're gonna do. Okay, and let me talk about homework. The homework too. So I did drop it onto Discord, uh, Tuesday. I think I dropped it onto Discord. But then the questions kind of came up. So either somebody missed that moment or wasn't here or something, and then looked where we've trained you to look, which is on Canvas, no homework too. So it's like success slash fail. So I just uploaded the homework to Canvas where it should have been in the first place if I was on my game and not trying to wrestle, the load that got dropped on me that I told you about. Okay, so homework 2 is up there, and then I swear on, I don't know, probably my mother. We'll go with my mother's grave because you know what I mean. I didn't like her that much. You know what I mean. So it's like, so I kind of, so it's a bet. It's a bet that if I break it, it's like, yeah, yeah. There are more sacred bets I could make. We'll talk later or not. Okay. Everyone's like, Dr. K, you evil satanic fool. Okay. So I think, as far as I can tell, that we got to about here. Does that seem right? Like we did representations of the number 5, and and then everything died, right? Yeah, that was the other part. Not only no audio, but so I have been buying equipment to stock this bag of goodness. Anyway, this is how far I think we got. Weren't we doing this stuff here? Like, yeah, we did all this. I know we did this, right? And did we do this one? Feels like we did. Largest value. Yeah, I'm sure we did this one as well. Yeah. And then obviously 0, lazy 0. And that gives us this idea. Okay. We did the interlude of how many bits in a byte. Okay. All right. Sorry. And when I went to do the second class with using just the slides on my Ironman USB drive, it was the wrong set of slides. So it was just a disaster. So
before you get going, I just had a question because I think you answered this last time.
Yeah.
On the homework, question number 1, when you say distinct combinations, is that just total integers that you can make?
Yep, same thing.
Okay.
Yeah, it's if I say 1 bit, how many distinct combinations are there? 2. How many numbers can I represent? 2.
So when you say n bits, it's just 2 to the n. That's
Yeah. Distinct combinations, right? Exactly. And really, and it's a broader idea. If I say you can represent 2 to the n numbers or integers, well, numbers of any kind, right? Because that maxes out all the possible combinations, right? If I say how many combinations of the bits, it's a broader question because they could represent numbers or something else, but they would still be unique combinations. If there were 2 bits, it would be 0, 0, 0, 1, 1, 0, and 1, 1. There would always be 4 distinct combinations as a broad idea. And what they mean, up to us. We get to decide. Okay, and then I'm going to do, let me turn this real quick. Just to make sure I've got, yeah, there we go. Something like that should sort of work. Yeah. All right. So we did this. Okay, hang on. Shoot, one more thing. One more piece of equipment. All right. Yeah, there we go. All right. So where we're at right now, we're going to talk about, so we did all that stuff. We started in, I think, on this notion of integer data types. And I think we got to like right about here. I think let's go with that. So some things about unsigned. We talked a little bit about unsigned integers to begin with, right? First of all, we're not talking about negative numbers. There are negative numbers, but in an unsigned integer, we can't represent any of them. We can't represent real numbers either. They're just integers. Why is this? Social contract. I think I mentioned that last time, right? There's a lot of rules and things we're going to talk about. They don't have to be that way, but it's just that's the social contract we decided on.
So what about that old argument if like 0 is positive? I guess it's like with 0, it's neither positive nor negative.
Zero means whatever we decide it means in whatever context we're talking about. Social contract. So that's the bottom line. But so we assume that everything is positive and that 0 is, in that set of possibilities, right? But there's certainly no negatives. We're not dealing with anything negative. So 0 is one of those, non-negative, positive, but for sure non-negative. As to whether 0 is positive or not, we can argue it.
So 0 should work well, or 0 should work fine if it's both signed and unsigned, right?
What do you mean by 0? Do you mean if it's all zeros, or do you mean any given bit, and then which bit are you talking about? Or the concept of 0? Okay, open your eye. I'm going to laser shoot it. No, these are, I think you're starting to noodle, and then we'll kind of go there. And then if at the end of that, the noodling is still, active noodle, then we'll go there again. All right. So with unsigned integers, what's the smallest and largest possible unsigned integer values? Smallest, easy, right? It's just everybody's 0. And the largest would be, well, what's the largest value in any given bit, right? It's going to be 1 on as opposed to off. Same thing if we're doing decimal digits, and we said, okay, I'm going to give you 5. I'm going to write a check for 5 figures, and you get to pick the numbers. Your number would be 999, right? It'll be a bunch of 9s because you want to max out every one, right? So we max that out by putting all 1s. You give me 8 1s, and I give you what number? Yeah, 255 is that value. If it's unsigned, we have a social contract about how to treat these values, right? We said that guy was worth the 1s, 2s, 4, 8, 16, 32, 64, the 128s column. And when you have one of each of those, you add them up, you get 255, okay? Because of social contract. So, oops, going the wrong way. All right, that's our range with unsigned integers. Now, this is one of those interesting things. Have you ever noticed this? That out in the world, people start numbering things with 1 because they're counting. Also, our fingers, 1, 2, 3. You don't usually count by going 0. How many people are there? You start, you were used to counting things, right? And out in the world, that's the biggest use for numbers. And then if we have to talk about 0, we just got, there aren't any, and it's like this discontinuity. Well, in computer science, that's not a discontinuity. 0 is your starting point. And there's some other things we'll talk about later when we get to things like jump tables, where you'll see that having things start at 0 actually make a great deal of sense in the context of computer science. So we're sort of unusual in the world because most people don't live their lives that way. But just a little interlude. Okay, it turns out that there are, in fact, in the world, negative numbers. Spoiler, foreshadowing music. There are, in fact, negative numbers. Now, we have to figure out how to represent them. How are we going to represent them? Well, we're going to try some ideas. We're going to establish a social contract and say, that's how we're going to deal with it. That's bottom line. And there are 3 in particular: Sine Magnitude, 1's complement, and 2's complement notation that are the classic ways of representing negative numbers. And we will walk through each of these. The ones that we really care about are sine magnitude and 2's complement. 1's complement is sort of like a historical side note. It was a short stop on the way to 2's complement. So we'll talk about it, but it'll never show up on the homework or the exams. Sine magnitude will, 2's complement will, but not 1's complement. But it is interesting from a historical perspective, okay? And then remember that you're still working with a fixed number of bits, like say 8 or 16 or some other usually combination of 8, right? Just remember that. This is not conceptual on the whiteboard. This is like given 8 bits, given 5 bits, given 16 bits, okay? Given some n number of bits. So another little interlude about representation, representing a number in a particular notation. Okay, and then I just want to reinforce this. When I say this number is in, if I give you a bit pattern, okay, like this I love you bit pattern, we can also think of as 11001, okay? We could say it means I love you in ASL, and that would be an accurate representation. But numerically, if we said, what does that number mean? If it's a negative number, how do we interpret it, right? Is it sine magnitude, 2's complement? The point being that the bits don't change. We can look at any given set of bits and interpret it as anything. The bits themselves don't tell you what they are. There has to be some other context that tells you, how to interpret it, okay? And the key is you have to design your hardware with certain assumptions built in. The social contract, in other words. Okay. Anyway, and as a byproduct of that, you have to think about how hard or easy it is to do certain things in hardware, and that'll show up as a thing. Okay, social contract. So here's an example. Anybody understand these two expressions by Winston Churchill, both involving raising 2 fingers? Do you know the difference? What's the first one? The one on the left. What is this one? No, I mean it might be jolly happy, but that's coincidental. What does the hand gesture mean? V for victory. That's what this one is. What does that one mean? Huh? It means this. Yeah, in British notation, let's call it. In America, we would go like that. We would put that one down. That's what it means. So in other words, the same 2 fingers up, 1-1, if you will, based on the social contract becomes a unifying. We win, V for victory, And then he did this to the press, so it's basically like you're walking out of whatever, and the press is just hounding you, and you just because this is Churchill, who just walk over and just go like that, and just like move on, He was not shy in that respect, okay? But that is what that means in Britain, which, okay, kind of cool. Point being, he basically did the same thing by holding up 2 fingers, but based on one small thing, the social contract, right? And by the way, this means peace in America, and that means the number 2 for the most part. If somebody's at the restaurant and someone's like, how many of those do you want? You might just go like that. Like, yeah, just 2. You like, yeah, 2. Or maybe you go 2, but it's harder to turn your arm around, so this is, right? And if you're like, peace, or there's this popular thing in Japan where the kids, they just love the peace signs, It's a big thing to do selfies with the Asian peace sign thing. Just saying that it has its meaning because of the social contract that we apply to it. There's nothing inherent or intrinsic in the fingers that have that meaning. We just decide that that's cool or exciting or vulgar or whatever. Okay? Let's do another one. different set of bits. 10010. Okay. What's it mean over here? That's a rock concert, by the way. What's that one mean? Yeah, rock on, dude. Like kind of bang your head. It's kind of like, yeah, you're just like that. How about over here in the middle? That's, that's hook 'em horns, right? Is that a like an A&M thing you do to insult Texas?
Like every Big 12 school just does horns down to like get at Texas.
Right. So yeah, so if you're a Texas fan, that's Longhorns, hook 'em horns, right? How about this is the Prime Minister of Italy, Berlusconi. Any guesses? No, no. Here's a hint. It's the same as Winston Churchill over here. Okay, that's an Italian gesture. The corn. It's called the horns, Interestingly, they're both horns. They're both horns, but these are called the corns, and it basically means like may your spouse be sleeping with the neighbor, depending upon the context, because it also has to do with the gesture on the face. Because if you're smiling, then it's more like doing this behind someone's head at the camera. And if you're angry, it really does mean, F you. So it's, again, kind of social context as to even what that means. Yeah.
I have some more if you want me to share, just like four more. Can I share?
Yeah.
Okay. So in the United States, this means okay.
Yeah.
In Japan, it means money. In France, it means you're a big zero. In Brazil, it means an insult like a middle finger. This one is you're a loser in the United States.
But don't you have to put it here?
Yeah, you can put it here. It doesn't matter. In China, it means the number 8. This one is you're good in the United States, and then in parts of West Africa, it's like flipping someone off. And then we already know what this one is.
Yeah. Nice. Yeah. Thanks for sharing. Right. Okay. The whole point is just to reinforce social contract. The same fingers, the same gesture, different context, different meaning. So when I give you a set of bits and I just say, what is it? The only safe answer is a set of bits. And then if I say, okay, it's a representation of an integer, you should have to ask, like, okay, signed or unsigned. If I say, oh, it's an unsigned integer, oh, I now understand the social contract. I can look at the bits and tell you that that's 24.
What about binary or ternary?
Well, yeah, no, if I say bits, I'm binary.
Yeah, okay.
Yeah, but right, you understand? And if I say, oh, it's signed, this is a signed integer, you got to go, what notation? Oh, it's 2's complement. Okay, now I can tell you that that's negative 45. But until I understand, so when I say it's a representation, I'm saying, what's the social contract I'm going to apply to this set of bits? Okay? Does that make sense to everybody? Okay. So we're going to start by talking about sine magnitude. This is one of the easiest, quickest, earliest ways of doing this thing. Start with an 8-bit byte, okay? So we got 256 numbers to work with. We're gonna allow negative numbers now. How are you gonna do it? And the reality is you could do it any way you wanted. I mean, when you're making the computer in the first place, when you're inventing this stuff, could have done it any possible way. So I don't know, it seems fair to say let's make about half of them positive and about half of them negative. I mean, that just seems only fair, right? If you don't want to, but you could do it where we'll allow 10 negative numbers and then the other 200 and 46 numbers will all be positive, and then there's 0, of course. I mean, what are you going to do? So I'd probably say half and half seems fair, but then you're still like, how are you going to do it, right? And all you're really saying is, what are the rules that we're going to apply so that we can figure this thing out? So one approach is, why don't we designate one bit to indicate positive or negative. We'll call it a sign bit. Does that seem reasonable? Now, here's the interesting thing. This is the hard part. You're like, well, but we are burning a bit, right? Now we're down to like 7 bits left. Say that again, louder, Miles.
You still have the same number of values you can represent those.
Right. No, exactly right. Because if I have one of the bits just tells me whether it's a positive or negative number, I still got, positive from like 0 to 127 and negative-ish, 0-ish to 127, similar ballpark. That's about 256 numbers. So weirdly, you'd think I'm losing I'm losing a value, but really I'm not. What I am doing is I'm creating a redundancy around 0, which we'll talk about. So that leaves me 7 bits for magnitude. Okay. Yeah. So how would you do this one? One is going to represent one of the two, either positive or negative, and the other one's going to represent the other one. And we get to decide. What would you do? Okay, open your eye. Open your eye. Right here, man. That would make it harder, yeah. Weirdly, that's why they didn't do that. But thanks for playing. No, what? We have a vote, and then there's only one other alternative, right? Which is 0 for positive and 1 for negative. Those are the only two possibilities. Now we can put it, let's address this issue of we're going to get to it. We're going to get to that. Let's just start with a bit that is the sign bit. What are you going to do?
Well, one's bigger than 0, so positives are bigger than negatives, so 1 positive.
That's I like the logic there. That's not bad logic. How many of you would vote for, what did you say? 0 is negative and 1 is positive. How many of you would vote for that?
I mean, if I were developing that, yeah.
And how many of you would vote for the other way around, where 1 is negative and 0 is, I think that's kind of 50-50.
Can I say why I would have 0 be positive and 1 negative?
Why?
Because until we hit past 7 bits, we can stick with unsigned notation, sort of mathematics, until we hit that 8th bit, and then we can worry about it.
Yeah, so it turns out that that's actually the logic behind it. If you allowed 0 to be positive, then until you got all the way up to positive 127, you could just treat it like unsigned, and the logic would already be built. Otherwise, you'd have to like ignore that 1 bit every time and have like 7-bit logic instead of 8, and the circuitry would maybe be harder. Yeah, Miles.
I mean, also like how I guess multiplication and addition works. Like if you're multiplying a 0, you would add it. Sorry, if you're multiplying 2 negatives or 2 positives, you just add the digits, I guess, and you get 0 no matter what. They're the same sign, right?
I did not understand that. Open your eye, Miles. We're going to shoot you with the laser. This is today's punishment for anything I don't understand. Permanent blindness. Open, yeah. Look into laser with remaining eye.
Hey, I've already looked into a couple of lasers before. They fixed my eyes, but that's beside the point.
Separate issue, yeah. Hopefully there was a doctor involved.
Yeah.
Okay, so Miles, do you want to double down on this, or do you want to pass and come back to it? All right. It's okay, but I mean, like, look, apart from the lasering your eyeballs, I appreciate the be thinking, trying, right? Because everybody, it's what they had to go through when they invented it in the first place, right? Had to be a thing. Okay, which do you choose? It turns out, well, then the other question is, where do you put it, right? Do you put it on the far left? Do you put it on the far right? Do you put a third from the left? Lose an eye over that one? Yeah. Let's talk about it. And an interlude about this terminology, high order versus low order. Okay? High order is on the left and low order is on the right. Okay? Why? Any guesses? Why would high order be on the left?
I would guess that because low order changes so rapidly, while high order not so much.
Okay? What's another way of saying that?
If we think of it as a number, we build a number out to the left, not to the right.
Yeah, keep going. What are the other ways of saying that?
It's like you're climbing a mountain. When you're on the lowest part, you reach that first. On the highest part, you don't reach that.
You get there slower.
You get there slower.
What's another way of saying it, Miles?
You're using smaller numbers more in low order maybe, so you don't want to put it to the far left because.
Well, we're not talking about where to put the sign. We're just talking about the terminology high order, low order.
What is high order and low order again? Do we know that yet?
No.
Okay, maybe just reading left to right. We read left to right, and that's why high would be left.
Okay, thanks for playing. Stare into the laser. No, keep going. Ding, 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 ding. Yeah. They call it high order because they're just worth more. Like if I've got 8 bits, right? And it's the ones, the twos, the 3, 4, 5. I'm an idiot. The 1, the 2, the 4, the 8, the 16, the 32, the 64, and the 128, right? That leftmost bit is worth 128. The rightmost bit is worth just 1. It's higher. It's just worth more. It's a higher value. So high order always refers to the left side because the values are bigger, right? You say I got a 6-digit check. You're going to try to look at the leftmost bit to see what the order of magnitude of that, right? Did you get $100,000 or $900,000? You care about the leftmost bit. You're like, oh, the change is 37 cents. You would never do that. If you did, laser pointer time. There you go. Okay. All right. So that's why we use that terminology of high versus low order, okay? Because I had asked this question. Hang on a second. I had asked the question, do you use the high order bit or the low order bit to use it as a sign bit, okay? And this is the interlude, okay? Leftmost bit is worth more. It's higher. Other one's lower. All right. Here's how we do it. Really logically, and I appreciate the incredible humor involved in third from the left. It's funny at a certain level, but obviously, kind of logically, you're gonna either stick it on the far left or the far right. Everything else would be goofy, right? Everybody kind of agree? You'd want to put it far right or far left. It could be viewed as a little bit arbitrary. It turns out that the actual decision about which way to do it, we use a sign lift on the sign bit on the far left. That's how we do it. In all of the signed integers in modern computers, the sign bit's on the left. Easiest way to build the hardware. You can do anything you want as long as you're willing to build hardware to do it. The easiest way to build the hardware is if it just turns out is if the sign's on the left. That's actually the answer. So now, and here's the outcome of the survey. Survey says 0 is positive and 1 is negative. And it really is that same logic that we talked about. Okay.
It's the easiest way.
Well, it allows everything to be unsigned until you get up over 127. If it's 8 bits, right? You can go from 0 to 127 and just treat everything like an unsigned value, which is super easy.
Can I make another argument for it?
Go.
Thanks for pointing in my eye. It's also easier to bug test because if you're going to hit an unexpected overflow, you're going to stay within the memory parameters as opposed to overflowing past it, which is useful.
Yeah, well, and it actually turns out that when we get to 2's complement, we start doing addition, and you get overflow, the sign bit gets used because you overflow into the sign bit, and then you mess it up. So you do things like add two positive numbers and the result is negative. You're like, hey, now.
It's designed for that. It's designed for it.
No, exactly. No, that's because when I do that, when I add two positive numbers and the outcome is a negative number, there was overflow into the sign bit to mess it up. And that's how I actually detect that there was overflow. Similarly, two negative numbers, and I add them together and my result is positive. This is a sign that there was overflow.
Is the point of a sign bit because a computer literally couldn't comprehend a negative number unless it had a bit to tell it like this, like
Yeah, the deal with the sign bit is minus something, no pun, minus some indicator. How you would just look at it and you have to make an assumption based on social contract. You know, so it's just going to look at it.
I think what I mean to say is like, is the sign bit there so that like a computer can associate these bits? Like, if we're going to do simple addition, it uses some bits to add, and then uses other bit. Like, I don't know, why would you ever need to say this bit is going to be negative? It's representing a number, and it couldn't figure out what a negative number is unless it had a bit to tell it.
Right. In the same way, if I write a bunch of digits on the board, and then there's no negative sign, right? And I just say, what's the number? Do you assume it's positive? Yeah. And then if I put a negative sign out the left side of it, do you assume it's negative? Yeah, because the numbers by themselves, if you came in and there was just a random smattering of numbers just on the board, and I said, what's the number? You'd like, which one? I don't know what you're asking me. But if they're lined up the way I expect them, and there's a minus sign, I go, oh, negative 3,400 and, whatever. It's all just telling it what it is so that it can do the right thing. I hope that kind of makes sense. It's a little funky. Yeah, yeah.
Is a computer at its fundamental level just really just doing addition?
Yes. Yeah. Everything math basically is addition. So if it wants to subtract some numbers, it takes, we'll get into 2's complement, but yeah, subtraction is just addition, and division is just subtraction, and multiplication is just addition, and all the other math functions kind of derive from that.
Division is basically how many times does this number add into this number?
That's right. So you subtract your way to glory on that one. Okay, so this is it. That's sine magnitude. The leftmost bit is the sine, and the rest is the magnitude. It's literally just like sticking a negative sign, and everything on the right is positive, conceptually, right? So that number right there, do I have that? Yeah, that happens to be positive 108, which if you want to go look at it, 1, 2, there's a 4, an 8, that's 12. No 16s, a 32, so that's 40, what did I say before? Plus 64, 108. And the sign is 0. That's it, sine magnitude. That one would be negative 108. You ready for this? I'm going to animate it. Ready? I'm going to animate it using my clicker. Positive, negative, positive, negative. You see the trick? You see the sleight of hand? Everybody cool with that? Okay.
Gibbs complement or sine magnitude?
Sine magnitude. Okay. So what's the range of possible values? But in general, sine magnitude in general. Now, here's what we did before. We did something like that, right? Like there's all of the, everybody's off, everybody's off. So in sine magnitude, what is that guy on the left?
1, 0. That's
right?
0.
Technically, it's going to be positive 0.
This is important.
It is positive 0. Okay, what's this guy though in sine magnitude notation? No. Negative all this crap. Negative 127. Now that doesn't look to me like the right range. We need the biggest negative number and the biggest positive number, right? To give me what the range is. It's not from 0 to negative 127. So you can't think of it this way. You got to think of it as the plus minus sign, the sign as it were, and then the remainder of the magnitude. So though you need the biggest negative number, the biggest negative number and the biggest positive number. That's your range for sine magnitude. Okay? So that just don't make no sense. So let's try this again. Let's take, you goes from 0 all the way up to positive, and what's this again? That's 127. So it goes from 0 to positive 127. Okay? And then it also goes from, yes, that is negative 0. What is the value of negative 0? There is no value to negative 0. I mean, it has the value negative 0. Socially, whatever. At a personal level, it has no value. I'd like to apologize to negative 0 right now. No, we're going to find out. Spoiler, 2's complement gets rid of negative 0 as being redundant and dumb. Okay, but it turns out that from negative 0 to negative what? Negative 127. Okay, because that's your sine bit and that's your magnitude. Sine bit, magnitude, sine bit, magnitude, sine bit, magnitude. Okay, that's why we call it sine magnitude.
So if you're writing out this in some magnitude, you just put 0 to the negative 0, it's considered wrong?
Technically, it's negative 0. It depends what the context is in which it's being considered. If I give you this number right here and I just ask you to tell me what its value is in decimal, I would take either negative 0 or 0 because they're functionally the same value. But Miles, there are situations in which recognizing that those values come rolling in differently makes a difference to something. You know, it really does depend on context.
So this can be simplified to 0 all ones to 1 all ones, basically.
Yeah, that's right. So the range exactly is from all zeros. Sorry. From all ones to 0 and all ones. That's the range. From negative 127 to positive 127. Okay? It's the biggest negative number, the largest magnitude negative number, and the largest magnitude positive number. Okay. Notations, interlude. Does it occur to you that you could use any pattern to represent anything? The problem is it just gets, why not just go totally random? Because it's confusing and dumb. What's that? Well, yeah, but the rule could be that this random makes no sense thing is negative 5. But define makes sense. Yeah. Well, yeah, the issue is lowering the cognitive burden. Like, for example, if there are rules that you can infer from, you can have rules that you can't infer from. Like every weird pattern is just a number assigned to it. There are rules. This pattern equals that number. That's the rule. But you can't infer anything because everything's random. A pattern of inference would be like, this pattern is negative 4, that one's negative 5. And you're like, ooh, I have not only the rule of what that value means, but the rule to derive the next one and to derive the next one. And it's cognitively easier. All right. Interlude, counting in binary. You know you've been waiting for this. It's not hard, but it's a little goofy. Counting, if you thought about this, counting is the same as adding 1. If I say count from 1 to 10, in decimal, you go 1, 2, 3, 4. All you're doing is taking each number and adding 1 to it. That's all. That's what counting is, okay? So we're also teaching you how to add in binary. Digits ripple left because of the carry. So there's 1, right? We add 1 to it. Now we're going to go to 2 next. What's going to happen here? What's 1 plus 1?
1, 0.
In binary.
1, 0.
Yeah. Another way of saying that is it's 0, carry the 1.
0.
Right? If I say what's 9 plus 2 and you say 11, that's correct. If I set it up and I go 9, 2, and put a plus, and I'm like, add these up, you would go 9 and 2 is 1, carry the 1 drops down, and you'd be at 1, 1. Yeah.
Did you see the GIF that is in the memes channel in the Discord? I think it really showcases this really well.
It's a really good gift.
I just feel like I'm being trolled all of a sudden.
No, I mean, let's be
No.
honest. I mean, let's be honest. Just pull up the Discord, go into memes. There's a GIF that shows this perfectly.
Yeah, it's really good.
And everybody can go scout that.
I'm not going to troll my professor because I like my grade.
Oh, no, I did see this one already. I did see it. Was it helpful?
I mean, I already knew binary, but it really does show that concept you're talking about very visually.
Yeah, yeah. Right. One of them is cascading, the other one's not. Yeah, okay, so the answer to this value plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. Okay? Now you're going to add 1 to that guy, easy, because the 0 plus 1 just gives you the 1, 1. Now you're going to add 1 to this one, and it's going to be 0, carry the 1. 1 and 1 is 0, carry the 1. And then your value is 1, 0, 0. There's 5. There's 6. I don't, in a very unsatisfying way, I randomly just stop at 6 for reasons that I can't explain at the present time.
How could you?
I did. Okay. Here we go. Let's do some addition and line it up, okay? 1 and 0 is 1, no carry. 1 and 0, 1, no carry. 0 and 1 is 1, no carry. 1 plus 1, 0. Okay, now brain pop, because I've got 1 plus 1 plus 1, and it's binary.
It's 1, carry 1.
It's 1, carry the 1, right? So I got a 1, and then I carry the 1.
And then that's going to be
Carry the 1. 1 plus zeros is 1. The zeros together is 1. That's the answer to that question, okay, of how to do binary addition.
Does that work if one's signed and the other's unsigned?
It does, well, we're going to talk about it. It does in 2's complement, which is the miracle. Okay. It turns out that if you can add a number to its negative and get 0, circuitry is easier. Let's do it. Let's try it. Let's do sine magnitude. There's positive 43 and there's negative 43. Let's add them together. I'm not going to walk through it all, but 1 and 1 is 0, carry the 1, 1, carry the 1, right, blah, blah, blah. It does not look like 0. So fail. Fail on the part of sine magnitude. Because what did I really do? What I really did was for the first 7 bits, I just added positive 43 to positive 43. Right? Like 86, right? And then just added those guys. So I actually get, in fact, I should have it there, but it's actually negative 86. Which makes sense if you look at it like what we're actually doing, but not real helpful. Okay? Now, somebody said, and now sine magnitude was known, and then somebody said, what if we just said, here, we like the idea that the leftmost bit is the sign bit. 0's positive, 1's negative. Well, what if we just took the value of some positive number and just like flipped all the bits. Because the sign bit would flip, all the other bits, well, like what would happen? So that's what somebody actually did, and they came up with this thing they called one's complement. If you think about it, that name makes sense, right? It's the complement of whatever the number is. If it's a 1, it becomes 0. If it's a 0, it becomes 1. That was the idea. Flip all the bits. So that would be a positive number, whatever that happens to be. 64 plus 16, which is 83. And then that would be negative 83. Okay? So let's try this one. Come on. There we go. All right. This guy here? Because he was that guy flipped. And that was our social contract. And that was our social contract.
That makes sense. I was looking at that and I was like,
Yeah.
that doesn't happen.
Yeah, because this guy over here is positive 83, right? Just because he's an unsigned value, like we expect. Because he's 0. At this point, do I care whether he's signed or unsigned? No, he's still a positive number, right? Unsigned means there are no signs. Everybody's non-negative. Everybody's positive. Signed means I've got that sign bit, but as long as he's 0, I just treat it like it's unsigned. I don't care. If I flip everybody, that's what I get. I can't look at that guy and immediately tell you what its value is. I can on the left. So most of the time, if I gave you a bit pattern and it was in like one's complement, and you wanted to know what the magnitude was, you'd flip all the bits and then like see what the value was, because you'd get it into the positive form. And we'll do that quite a bit. It's a little clunky, but it actually works. Okay, so let's do this. Now there's positive 43 right there. There's the 3, and there's the 16, and 1, 2, 4, 8. Am I doing this right? 32 and the 8 make 40, and then the other 2 make 3. So 43. That's just flipping all the bits. Let's add it up. What are we going to get? All ones. It's going to be all ones. That's negative 127, which is conspicuously not 0.
So what's the point of one's complement?
It gets us to 2's complement. Because there were machines that were built to do this. But what they've realized was, what would I have to do? Just think about this for a second. To that number to turn it into a 0. I could do a couple of things. I could flip all the bits, I think is what you said. That would turn it into a 0. What else could I do? And what else? Well, ignore the carryout. In other words, ignore the overflow. If I added 1, I'd get 0 carry the 1, 0 carry the 1. It would ripple until I had 8 zeros. And as long as I ignored the carryout, the overflow, I could get to 0. So this is actually where we go. Yeah.
Hey, if we're going with one's complement, shouldn't the answer also follow one's complement? So in that case, it would be negative 0.
Well, that's the other problem is, which 0 do we want? Positive 0 or negative 0? It doesn't, at some level, it doesn't much matter. But when they were doing the circuitry for one's complement, somebody said, look, we can always fix it. Every single time we get the wrong answer, but we can always just fix it by adding 1. It's always 1 off. You know what I mean? I'm always going to fix it by adding 1. And then somebody said, okay, what would happen if when we represented a negative number, what if we baked in the adding 1 whenever we made a negative number? What if we just added 1? What would happen? And a miracle. It was a Christmas miracle. What's that? No. No, leftmost is still a sign, but we do ignore the carryout when we add one. So somebody said, okay, what would happen if we, instead of waiting till we got done adding numbers, right? We just, every time we made a positive number into a negative one, what if we flipped all the bits and added one right then and baked it in? So every number, every negative number was already a positive number with all of its bits flipped and one added to it, and ignored any overflow if it flowed out. That was really the idea, okay? And everything was amazing after that, okay? Um, to his compliment. Cue the theme music. Um, yeah. So here's the thing with two's complement. It is really just this idea. Instead of waiting until you do a math problem, bake it into the number itself. You want a positive number? You want to turn it into a negative one? Flip all the bits and add one right then. Okay. Now here's the amazing part. What if you wanted to change it back?
Flip it, subtract one.
So close.
Oh, subtract first.
I said it was a Christmas miracle. You flip it and add freaking one again, and it just flips. The whole number just flips from a positive to a negative to a positive. And what if you then just take these numbers, whether they're positive or negative, and just add them together? They just do it.
You're basically overflowing into it.
And you always have to ignore the overflow whenever you're flipping and adding one. You always ignore the overflow when you're doing that operation. Okay? Isn't that weird? It's crazy. I know it's math. I'd like to thank the universe for this thing that just happened to be a thing. Um, yeah. So this is too many words for one slide. But remember that when you're doing two's complement, positive numbers look just like unsigned integers. They look just like sine magnitude integers because the leftmost bit is 0, and the rest is just somewhere between 0 and 127. All right. But then where it gets interesting is the whole negating a number, right? Now, this is terminology. You got to track with me on this one. Negating a number does not mean making a number negative. Negating is the process by which a positive number becomes negative or a negative number becomes positive. So if I say negating a number, I'm saying changing its sign. Positive 10 becomes negative 10. Negative 10 becomes positive 10. That's negating. If I say make a number negative, then I'm asking for negative 10. Okay? So, all right. Let me see. In decimal, right? We have this no minus sign means it's positive, and the minus sign means it's negative. How do you negate a number? You just change the minus sign, right? It's decimal is sine magnitude. Okay? Our decimal system is sine magnitude. Negative 10, how do you represent it? A sign and a magnitude, right? The sign is a line or no line, but there's a sign. Okay? So here's what we do. This is just a repeat. You represent the positive number. So if I say the value 10, decimal 10, and I say, give me that thing in two's complement notation, you would just represent it, and it would start with a 0, and it would have the magnitude 10. It would look like sine magnitude. It would look like unsigned because it was positive 10. You would then flip all the bits. Every bit gets flipped. And then you'd add 1 to it, and that would be negative 10. And interestingly, the leftmost bit will be 1. It'll tell you it's a negative number because the leftmost bit will still be 1. Isn't this kind of like just freaky and cool? Or just creepy, but cool? Okay. Yeah. Okay, let's do it. Let's take 83, our old friend. There it is. We trust ourselves, right? 64 plus 16 plus 3. We're going to turn that into negative 83. we are going to, there we go. I'm going to flip all the bits. And then I'm going to add 1. That is the representation of negative 83 in 2's complement. What's that? And you can't just look at that. There is mathematically ways of looking at that and telling what the value is. But it takes a few extra steps, and I don't even want to talk about it. Because if you already get it, good on you. If you don't, let's not even mess with it.
So to get back from the negative to the positive, we just subtract 1 and then flip it again?
No. You flip all the bits and add 1. So the negating is always, meaning it's you do the same thing every time. Isn't that crazy? That's crazy. I've been teaching this for a while and have known this for a long time. It's still crazy to me.
So for the negative, the leftmost bit will always be 1. So we can identify it, and then we got to start looking, if it's a 1 at the beginning, then we got to add the 0.
If you want to know what the value is, yeah, if you want to understand, like, I see this negative number down here and I don't know what it is. Like, well, I can flip all the bits and add 1, and then I'm like, oh, it's 83. Oh, that other number was negative 83.
Also, they mentioned the last part of the previous slide about if all the numbers are 1, you have to keep going to the left and ignore it. Would that be if you flip a bit that's all zeros?
Well, yeah, we'll get to that one when we start with all zeros, okay? Because there's one exception in all of this, okay? So now let's start with the negative. That's the value we just created, okay? Everybody buying? There it is down there. And there it is up there. We are going to flip all the bits. You see it? And we add 1. Joink.
So the first number is always positive, right?
No.
No.
It depends on what you mean by that. Any number in 2's complement notation could be a positive, could be a negative. If I want to change the sign of the thing, right? In decimal, I would just add a negative sign, or I would erase a negative sign. If I want to do that same operation, all I do in 2's complement is I flip all the bits and I add 1.
So in unsigned 1 0 0 0, so 1 0 0 0 is 8.
Okay. Do you
Signed,
mean that the other way around?
So in signed, it's negative 0, and in 2's complement, if we flip it, it's negative 8.
You've got, okay. First of all, how many bits are in your byte?
We're talking about the homework.
Okay, good. Yeah, so you're talking about 1000, 4-bit byte. And it's Sine Magnitude? But is it all the different versions? Is it asking you, like, what's that in Sine Magnitude? What's that?
So there's 3 different ones. So in unsigned, it's 8. In signed, it's negative 0. And in 2's complement.
Yeah, let's just look at it if I can find my markers.
I just don't know if we flip this to 1 or if we just leave it and then flip it.
Okay, so we've got we've got that number, right? So let's start with the ones that are really, really easy. Let's go Sine Magnitude. What's its value in Sine Magnitude? Right. And by the way, we're talking about 4 bits. Right? Could have been 8, but it's 4, right? So in Sine Magnitude, it's negative 0. What's the other one it wants? Unsigned? What would it be in unsigned? Correct. You could say positive 8, wouldn't matter, right? We know what the value is. Okay, 2's complement. Well, you know it's a negative number, right? How do you know it's a negative number? Sign bit. There's a sign bit. So first thing to do, put a negative sign. Start by putting a negative sign. Now I got to figure out what the magnitude is. What am I going to do?
Negate it,
I'm going to negate it.
and then add 1. And
Now we're actually ahead of the slides just a little bit. It turns out we're going to get to this, okay? But not right this instant. Because this is the one exception where there's a value. And now let me see. Spoiler alert. This thing is going to go, the range on this guy goes, in sine magnitude, the range goes, in this case, would be from -7 to +7, right? Unsigned, the range is from 0 to 16. No, 15, sorry, yeah. 15. It turns out that in 2's complement is from -8. And there's always, in 2's complement, when you get down to the lowest negative number, there's an exception right there. So the actual value is -8. But it's the one spot where the rule doesn't quite hold. But if you use it for math, it'll work.
It kind of does if you're making an assumption based on the unsigned value.
Ish. We'll get to it. Okay. Let me keep going because we really will get to it. And way to play interactive homework bingo. I mean, this is always appropriate. If there's something that's like, wait, that didn't help me and I don't understand this.
So that number in 2's complement is -8.
Right? It's like, okay, but that's the weird exception. Because you'd buy -7, right? See, do you see how screwed up your mind has become? You're willing to accept -0, but -8 is throwing you off. That's what I've done for you today. Here, let me gouge my eyes out with a laser pointer. Yeah. The lowest possible negative number, no matter how many bits there are, which we're going to get to as well. Yeah. That's right. If you've got 8 bits, it's going to be essentially -2 to the n on the low side, and then on the high side it's going to be 2 to the n -1. Actually, it's going to be negative. Let's not even go there. 2 to the n -1, and then that quantity, same quantity, -1 on the high end. Okay, let's keep going and see how far we can get because we're not going to get all the way through. We'll wrap up on. Well, we won't be done, so we'll just delay the homework. I mean, we'll delay the hard deadline of Sunday. If I don't finish any, the slides for a particular homework by Thursday, then we've got to cascade it out to the next week. To be fair. Correct. There's only straight up 0. Okay. Oh yeah. Oh yeah, let's do this. So we did that one. Now let's double check it. Let's take +83 and -83 and add them together. 1 and 1, and you can just walk through it. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. That pattern just repeats until it cascades out and we ignore the carry out and the value is 0, which is just freak. Okay, modern computers use 2's complement, but it's been around for a very long time. Okay, So why pester you about sine magnitude? Sine magnitude does actually show up under certain circumstances, and was complement never does, but it's a stepping stone. It's a gateway drug to 2's complement. Okay. Okay. Here's where we're going to go on this last part, and we got time to hit this, so that nobody has to go home in trauma. When you change from sine magnitude or 1's complement, going to 2's complement, you pick up an extra positive number or you pick up a negative number because you pick up an extra number. There's no negative 0. Sine magnitude has a negative 0, right? 1's complement has a negative 0. When you go to 2's complement, you don't have a negative 0. So you get to decide, we got an extra number, right? We got a spare number. What do we want it to be? And the answer is, we'll make it the smallest negative number, the largest magnitude negative number. Yeah, and this idea of the high order bit is still the sign. In 2's complement, high order bit is still the sign. There's really a couple ways to look at it. One is a positive number always has a 0 for the sign. Flip all the bits and add 1, except for that extreme negative number. That 0 is going to turn into a 1. It's going to stay negative. But you can prove it out. The way to prove it to yourself is to just do this right here. You're going to add it together. It's going to turn into 0. Okay. Let's review. What's the largest of 8-bit 2's complement number? Positive 127, right. What's the largest negative?
Negative 128.
It's negative 128, and that's the weird part. Just like this guy, and negative 128 is going to be.
Well, 0 is still an integer that you measure.
What's that?
0 is still an integer you measure.
What do you mean by you measure?
0 is still takes the place of one of the possible combinations we have.
Okay. Let me see if I can get to this part. What's the range of numbers that you can represent? Let's just hit a couple of these. I should have it. Okay, let's talk about this one. The way to reason this out, the largest positive 8-bit number, you got to know that the leftmost bit has to be a 1 because it's a positive number, right? So there's your 0, but what's everything else? All 1s. Give me the biggest number, right? What do you do with the remaining? So therefore, you look at this and you add them all up, 64, 32, 16, 8, 4, 2, 1, and you get 127, okay? So that's the largest positive value, okay? Largest negative bit value, negative 8-bit value. Let's try negating 127, okay? We take that value, we flip all the bits, we get this, and we add 1. How are we doing? Well, let's test it. The reality is, at this value, so that is negative 127, okay? And if we add these two values together, we get back to 0. But what would happen if we subtracted 1 from this number? Would it be fine? So this value we know to be negative 127, and there is one number that's smaller than it. By subtracting 1 from this number conceptually, right? What if you subtract 1 from this number? Negative 128. That's the logic behind, like, we'll just make that last one when you subtract 1. It looks like negative 0, but that is the representation of negative 128. And then the weird dynamic is there is no positive 128 in 2's complement with an 8-bit number. So if you start with negative 128 and you flip all the bits and you add 1, you get to negative 128 again. Because there's no 127. There's no positive 128. Hope that makes sense. Yeah, so that's how we do it. Ignore the carryout again. Take that value, subtract 1. This, by the way, is negative 1. If we actually do it, if we take negative 127, we agreed that was negative 127, right? And this is -1. I can prove it by give me all zeros with a 1 at the end, all zeros and a 1, right? Flip all the bits, I get all 1s and a 0, and then I add 1. What do I get? All 1s. So in 2's complement, every time you see all 1s, it's -1. So I add these values together. 1 and 1 is 0, carry the 1, 0, carry the 1. Cascades all the way out till I carry the 1, and I get 1, carry the 1, and I ignore the carry. And I can actually take -127, and I can subtract 1 from it, and I can get to -128. So it's a little bit of a magique, but you can sort of get there. That makes sense. And then we already did this one where we took -128. We got back where we started. All right. So that's our range from -128 to +127. And then I'm saying do this for 2, 3, 4, and then n, which is where you're at the homework. Okay. We're going to come back. We're going to be right here on Tuesday. We'll wrap up. We'll push the deadlines for homework and module exam, just to be fair, since we didn't finish the lectures on it.
Was there any logical reasoning as they were doing this that since half of the numbers are negative and half of the numbers are positive, we want to solve -128, we just add half of the range of